Добрый день, уважаемые слушатели. На прошлом занятии мы рассмотрели, как установить пробную демо-версию термокалк на компьютер, на программу Windows, и посмотрели пробное вводное занятие. А сейчас мы рассмотрим следующий урок, где говорится о том, как рассчитывать фазовый состав с помощью данной программы.
This video will show you how to create a phase transition calculation using the property model calculator in the graphical mode of thermocalc. In this example, we're interested in finding the phase transition temperature of sigma and how it changes with variations of material composition, as it is brittle and generally undesirable. The calculation is based on the property model example General O1 of the examples included in your software. The example used to be called example T10, but has been renamed to clarify that it uses the property model calculator. You can access the example in the Help menu, Examples files, Property Models, General. If you are using an older version of thermocalc, this example is located in the thermocalc folder under T10. To begin, select the one-axis equilibrium template from the home screen of thermocalc. This template used to be called Property Diagram, so if you have thermocalc 2019A or older, click on the Property Diagram template. The calculations will be the same, only the name has changed. We want to make a one-axis calculation first so that we can get a good starting temperature for our property model calculator. From the Database drop-down menu, select the FE Demo database, then select the elements iron, nickel, carbon, manganese, and chromium. Next, we'll set our composition. Iron is dependent, so we'll let that set automatically. Nickel is 1.4, carbon is 0.08, manganese is 1, and chromium is 17. This sets iron to 80.52. If you use the same materials repeatedly, you can save them to quickly load them in the future. To do this, name the material whatever you like. I will call this one ferritic. Then click Save Material As. Decide where you want to save the file, and click Save. Next time you set up your calculation, select your database, then click Load Material to retrieve the file you just saved, which will automatically load your elements and composition. Next, we need to configure our calculation, so select the Equilibrium calculator. Notice that the composition auto-populated here. Set the temperature unit to Celsius. We'll use the default values for temperature, pressure, and system size, so make sure your values match mine. Next, we will change the axis definition so we get a better view of the plot. Set the minimum temperature to 400 and the maximum temperature to 2000. Our calculation is now configured, so select Perform Tree at the bottom center of the program. Once the calculation is complete, a plot will appear in the results pane. We are interested in the sigma phase, which is represented here by the dark green line, so I will drag my mouse over the area to maximize it. When I hover my mouse where the sigma phase appears, we can see that the transition temperature is at about 599 degrees. If you are using an older version of thermocalc, it may appear to be closer to 596 degrees. Either way, we're going to round up to 600 degrees for the starting temperature. Remember the number 600 because we'll use it in the property model calculator. We are now done with the one-axis calculation, so right-click on the system definer, hover over Create New Successor, and select Property Model Calculator. We are doing a phase transition, so click the Phase Transition Model. A tab will appear where we can define our conditions. Notice that the composition we set in the system definer auto-populates here as well. We just learned from the one-axis calculation that sigma forms at about 600 degrees, so we'll set the temperature to 700 degrees Celsius to capture the temperature we want. Because we are looking for the phase transformation for sigma, we want to calculate from any phase to sigma. We want to vary the temperature, and we want the search direction to be positive to negative, so set the direction as negative. If you are using an older version of thermocalc that is asking for a search range, set the search direction to positive and negative, Set the lower temperature limit to 400 degrees and the upper temperature limit to 700 degrees. Then change the temperature at the top to 600 degrees. Next, we need to select our calculation type. We recommend that you always run a single calculation first to make sure the calculation is valid. So select Single, then select Perform. The calculation will run in the event log. When it is done, the last line of the event log will read, "The sub-process completed normally." If the calculation worked, you will see the result called the relaxed condition. The relaxed condition refers to the variable, which in this case is temperature. We got a temperature of approximately 599 degrees, which is the same temperature we saw in the property diagram, and is the temperature around which our plots will be based. If the calculation did not work, you will see NaN, which means not a number. If this happens, check your configurations and run the calculation again. Because we got a number, we know that the calculation was successful, and we can move on to a more complicated calculation. Select the uncertainty calculation type, which allows you to add variations to the configuration. We want variations in our composition, but not our temperature. So check the boxes next to each element. Starting from the top, nickel is 0.4, carbon is 0.02, manganese is 0.3, and chromium is 2. We will accept the default parameters of a standard deviation of 3, but we will change the total number of samples to 40. To learn about the sampling parameters, visit the online help by clicking Help, Online Help, then searching for sampling parameters and selecting About the Uncertainty Calculations. Lastly, we need to add a plot renderer. So right-click the Property Model Calculator node, hover over Create New Successor, and select Plot Renderer. Next, right-click on the new Plot Renderer node and select Perform Now to run the calculation. We can see from the events log that the calculation is probably working because the temperatures shown there are all around 600 degrees. Once the calculation is complete, a histogram, also known as a frequency diagram, will appear in the results pane. The plot tells us how the transition temperature of sigma varies when we vary the composition. The plot will be slightly different each time you run the calculation because it is taking a random sampling from the composition range we set, so your plot may look slightly different from mine. Notice that the x-axis is labeled the relaxed condition. We can see which condition is represented there by looking at the condition to vary. In this case, it is temperature, so the x-axis shows us the temperature. The y-axis shows us the frequency, which is the number of samples out of 40 where the composition transitions at each temperature. We can see that the transition occurs more frequently near our 600 degree starting point and less frequently at the edges. Again, the variations are based on the varying amounts of the elements that were sampled from Gauss distribution functions based on the deviations we set. For a detailed description of this, again, visit the online help, search for sampling parameters, and select About the Uncertainty Calculations. You can see whether the plot follows the Gauss distribution by clicking on the Plot Renderer node and changing the y-axis to normal probability, then clicking Perform again. You can see that our data follow the Gauss distribution fairly closely in the middle, but less so at the ends, which is to be expected as there are fewer data points at the edges. To learn more about the Property Model Calculator, view the other examples videos we have available by clicking the links currently on the screen, or view our user guide which explains how to set up calculations in all the models.
Спасибо за внимание.